Thank you for coming. I'm very excited to introduce Pradeep Ravikumar, who is here from UT Austin, where he's an assistant professor of computer science and also affiliated with the Division of Statistics at the school. Pradeep has done extraordinary work in the area of very large-scale machine learning, especially with very high-dimensional data sets. He got his PhD from Carnegie Mellon, working with John Lafferty and Larry Wasserman, and then did a postdoc in Berkeley, working with Martin, I guess Martin Wainwright, BNU a little bit, and BNU. So he's been on the fringe between statistics and computer science from the very beginning. Now as a professor, he's done a bunch of new things and even gotten the NSF Career Award. With that, I'm very excited to have you here and listen to what you've done in your latest time. Thank you.
Thank you, and thanks everybody for coming here. I'm glad to be here. So today what I'm going to talk about is statistical machine learning for big P, big N, and complex data. So I'll define what these terms mean. So first, what is statistical machine learning? I'm sure many of you know this, but let me spend a slide anyway. But first, what is machine learning? Machine learning is something very simple, or at least its goal is simple as it is, I guess, profound, because it's inferring conclusions from data. That seems very broad, right? And in recent years, people have been talking about machine learning and data applied to science. So people have been talking about data-driven science as a whole new paradigm of scientific discovery. After empirical, theoretical, computational, and now people are talking about data as a whole new way of doing science, which is great. And of course, you also have data-driven engineering, where people want to use data to figure out how to optimize their engineering processes. So we have so UT Austin is, or Austin is, and the general area is actually the original Silicon Valley. We have a whole bunch of chip manufacturers there, AMD and so on. And a lot of those companies, Freescale, AMD and so on, so what they really want to do, and they talk to us, they have their whole engineering assembly line and pipeline, and they want to use data analytics to optimize that. Even such well-established companies, they want to modify the engineering processes using data. So data-driven engineering, and just last week, I think David Brooks came up with this notion of data as a whole philosophy on its own, where you use data to try to predict the future, and it's a whole new way of thinking, a whole new philosophy. So that's machine learning and working with data. And what is statistical machine learning? Statistical machine learning is a subfield where you use statistical models, which is the infrastructural element that it's based on, where what it really is that you have a whole bunch of variables in your system. Any system, you characterize it as a collection of random variables, and you specify or model the probabilistic relationships amongst those variables. So that's statistical machine learning for you. So from the previous slide, it's science, engineering, philosophy. It pretty much covers everything. So as you can imagine, it has a whole bunch of applications. So in almost anything, they say that you're doing something important if you're curing cancer. You're doing machine learning, are you curing cancer? Well, maybe I am, maybe we are. So given a tumor, you can try to predict whether it's benign or malignant, for instance, which is more diagnosis, but you can also look at cancer patients and their genomic markers and genomic information, and you can try to fit statistical models to characterize their genomic data. Right? So in fact, we just recently had a oral presentation at NIPS which really came out of some work we are doing with the Baylor College of Medicine, where they were looking at some cancer data, and they had a whole bunch of count data, which comes from really next generation sequencing technologies. And they wanted to fit complicated graphical models, but it turns out that we really need to go back to the drawing board and come up with a whole new class of graphical models. So curing cancer, okay, so that's a checkbox that machine learning will eventually take. It's not there yet. Of course, you have medical diagnosis, drug discovery. That's also something that I've recently started looking at, which is what people are interested in is, so in drug discovery and development pipeline, given any virus, they want to figure out the structure of the virus so that they can come up with something that matches the structure of the virus. And so in a lot of movies and a lot of serials and so on, they always show you the structure of the virus, and these really small agents. And I always thought that was representation to a very high fidelity. Optical microscope, but you still know the structure. It turns out all of it is really a mathematical approximation. We don't really know what the structure is of the HIV virus to a really high fidelity. Right? So we need state-of-the-art machine learning to figure out the structure of the HIV virus. Right? And so this is something that we can make advances towards. And of course, you have bioinformatics, which has been with us for a while. And I've done work on estimating the association structures amongst genes and proteins and so on. And of course, you have a whole bunch of engineering applications, text, speech, vision, and broadly within AI itself. And so we have Russell and Novick, in their book, they call it the statistical revolution in AI, the whole statistical machine learning field. And the victory of the neats. So I know many of you know, but there are two camps, neats and scruffies in AI. And they said the statistical machine learning is really a neat methodology. By neat, they mean mathematically rigorous. And that it has really made a lot of advances in AI itself, which is great. Okay, so it all seems like a fairy tale, right? Science, engineering, philosophy, curing cancer, and so on. And in any fairy tale, there is a villain. An evil wizard, evil witch, and so on. And the evil wizard in this fairy tale is modern data. So modern doesn't seem that evil, so maybe I should say postmodern data. So what is modern data? Well, modern data is what people also call big data, where you have a lot of features, a lot of observations potentially, and the observations are complex. So you can have data that's from the brain, measurements of the brain using fMRI, which is a non-invasive way to figure out what we are thinking. So be careful. And gene expression data, a lot of genomic data. Social networks, where literally I have billions of nodes, and I need to figure out how people are acting together. Right? So it's a huge, huge data source and a source of problems. Okay, so that's modern data, that's big data. What can statistical machine learning do for this big data space? Right? Because statistical machine learning has been there before this whole advent of huge amounts of data. Right? So first, let's look at what really are some of the characteristics we're going to look at in this talk. So one is big P data. So P indicates the number of variables in the system, or the number of features, if you will. Okay? So if I have too many features, I call that big P data. Okay? So that's sometimes also called high-dimensional data in statistics. So then I have big N data, which is where I have too many observations. Right? So that, again, I can imagine, this doesn't happen a lot in scientific settings, but for instance, imagine the Large Hadron Collider, where I get a lot of data every second, gigabytes, terabytes every second. So that's big N data. And I can also have complex data, where the data is not really huge in size, it's not huge in number, but the data is complex. Think about the structure of the HIV virus, for instance. Something very complex. And largely, these are objects that lie in a complicated, discrete space. You can even look at permutations. So these are some facets which make big data problematic. And so this whole thing about scruffy versus neat and the cheerleading, if you will, that statistical machine learning can do great things by being mathematically rigorous, modern big data is throwing a crutch in that story, because frequently state-of-the-art methods are proving insufficient. I mentioned that stuff we were working on with, briefly, that I'm working with on some cancer data, and state-of-the-art graphical model estimation procedures didn't work. Right? So we needed a whole new way of doing things. So that's what machine learning has to do. So, okay, so let's ask this question: how can statistical machine learning help in dealing with big data? So the first approach is to really reach across outside machine learning, and that's to look at systems-related approaches. So you can look at parallel distributed algorithms. So I have algorithms that can learn a statistical model, but maybe I can try to parallelize it, try to make it amenable to distributed across clusters, right? And so on. And not just the algorithm itself, but even the data itself. If I could store it in a distributed fashion, that would be great. I know that Carlos is doing great work, and even UC Berkeley is doing some very interesting work on taking systems-related research and merging it with machine learning research. So this is one space in which statistical machine learning can be extended to work with big data. The other is optimization-based approaches. So optimization is actually a key part of what folks in machine learning do. So I have this huge statistical model, and I want to learn it from data, right? So I want to learn the weights, maybe some functions, and so on. And this learning problem is frequently reduced to an optimization problem. Okay? And if I have a large-scale statistical model, I have a large-scale optimization problem on my hands. And large-scale optimization is something people have worked on a lot, and folks in machine learning are also working on a lot in recent years, including myself. So again, here I've reduced it to a large-scale optimization problem. Let me set about solving large-scale optimization problems. Of course, it has some structure because it comes from statistical estimation, and that's what makes it interesting, right? And so, for instance, first-order methods, which are just methods like gradient descent. So if you have taken an optimization class, gradient descent is something that teach you first off, and it's like, okay, let's go to more interesting methods. In large-scale optimization, such simple methods are the only things that work. Right? So they have had a resurgence of popularity in recent years. But I should mention that what I've been working on are more complex methods, like second-order methods, greedy methods, divide and conquer, and so on, which are computational schemes that we use without a second thought for medium-scale problems. But what we are showing is that we can also extend these to large-scale problems. Okay? So this is another huge area of research that a lot of folks are engaged in, and this is one way to port machine learning and make it amenable to big data. But there's one other arm of research in which we can do statistical machine learning that's amenable to big data, and that is to stick to statistical modeling. So I still want to fit a statistical model over 1 million variables. Can we do that? Right? So tune the statistical modeling to specific aspects, specific facets of my big data, and ask the question, can it be done? Okay? And so that is a prime arm of my research, and that's what I'm going to talk about in today's talk. Okay, so first let's look at the first component, which is big P data. Okay? Let's see what big P data is. It's really high-dimensional data. I have too many features. Okay? Simply, that's the problem. Too many features. What do I do? Well, we have something known as a curse of dimensionality. Okay? So if you have lots of features, learning a statistical model over these features, even something as simple as linear regression. Right? So if I have 1 million features, linear regression has 1 million weights. Just learning 1 million weights from very few samples gets tricky. Okay? So even but if I go to more complicated statistical models, things get very, very unwieldy. So what can be done? Right? Can we do something? So again, to some degree, big P data has been with us in some guise or the other, right? Even 10, 20 years back. Right? And so what did people do then? What people did was they took their 1 million long feature vector and projected down to some smaller dimensional space. Right? So maybe take some random projections. Maybe do some feature selection. Feature selection has been with us for a long while. Right? I have 1 million features, let me just pick 100 features and call it a day. Right? In some intelligent way, but that's something I could do. Right? Slightly ad hoc, but hey, that's the only thing you could do. Is there something else that one can do? And the answer is yes. And this is research over the last decade that has really put this to the fore. And really catching steam within the last 5 or so years. And now we know how to fit in situ high-dimensional models. So I have 1 million variables, right? So I can actually fit a joint distribution over 1 million variables without any projection, ad hoc feature selection, and so on. Okay? So that's the task of big P statistical machine learning. So, so how do I do that? Right? So there's been a surge of research, as I mentioned, and all of that really correspond to what is known as structurally constrained models. They have some structure in mind, like Sparse, which is essentially compressed sensing. You have low-rank structure. You have graphical model structure, which is the association structure connecting the different variables. And we're going to look at some of these in the slides to come. These are certain structural assumptions. So you have a certain language to constrain your large statistical model. And under such constraints, you can now learn the statistical model using very less data. Okay? So that's something that we have just realized over the last decade or so. So discrete graphical models. Graphical models, again, have been with us for a while, but now we know how to fit large-scale graphical models. So here is an example that many of you might have seen, so here the variables are US senators. And I want to find out the association structure among the senators given their voting records. Right? So this isn't so high dimensional, just 100 nodes. But I can imagine more complicated social networks with literally millions of nodes. Right? So this is a simple social network, and you can see that there is, so you can use state-of-the-art statistical estimation techniques to learn such graphical models. And you can see that the reds and the blues really cluster with each other over there. So of course, so that's discrete graphical models where the variables are discrete, but you can also have such association structures for real valued variables, which is most scientific data, like genomic data. Right? And you can still try to fit, so let's say I have 10,000 genes, right? And I have their expression levels measured using some technology that gives me real values. I can try to find the association structure amongst all the genes. Scientists love that, right? So that's what they call genomic pathways. They want to find out, is this gene really directly associated with that gene, and so on and so forth. And if you can do this for large-scale settings, genes, genomic fragments, and so on, that would be great. Right? And we can do that now. And all this is very recent. Okay, so that is graphical model structure. And the other is just simple linear regression. Okay? Linear regression is something that has been with us, I think, ever since Gauss, really. It's where I have a response y, I have certain features x, and I have a signal theta star. Okay? And so y, the response, is really a linear function of my signal plus some noise w. Right? It's a very simple model, linear regression. Right? So we even study this in high school. And it has a humongous set of applications. Right? So you can try to predict almost any variable of interest given certain features by the simple model. And so what's new here? The new thing comes where the signal, theta star, is high dimensional. So if I have 1 million features, right, and I try to predict certain responses, y, say housing prices, and I only give you 100 observations, can I still estimate these 1 million weights from 100 observations? Answer is yes. Okay? And there's been a lot of work, again, over the last decade on how to do that. And you might ask, okay, how do I do that? Right? And the way people have done that is by imposing structure. So if you look at the vector theta star, if I assume that very few of its entries are non-zero, right? Let's imagine that I have 1 million long vector, but only 10 of its entries are non-zero. Right? 1 million minus 10, everything else is 0. If I knew which 10 to focus on, I don't have a 1 million dimensional problem, I have a 10-dimensional problem. Right? But suppose I don't know that. So there's still some model selection. But I still have imposed some structure. Right? I'm saying that this is a model selection problem you need to solve. And we know how to do that. And low-rank structure is another kind of structure that comes up a lot in the Netflix challenge, for instance, and a whole bunch of other problems, where my parameter, theta star, of my statistical model, and it could be any statistical model of interest. Let's say the weights that I care about are in that matrix theta star. And if that has low rank, and low rank again is something we study in high school and early undergraduate studies. So it's just the assumption that its row and column spaces are lower dimensional, right? So just under this assumption that the parameter matrix is low rank, I can learn these weights. So again, suppose I have a K by M matrix. I have Km weights, Km real numbers. I need fewer than Km observations to figure out these Km numbers, which is great. This is just to give you a very high-level view that, okay, so there are certain structures that people impose on their models, like sparsity, which is that very few entries are 0, low rank, which is that the matrix is low rank, and so on. Graphical model structure, where the association graph between variables is sparse. And what people have shown through a large set of papers is that if I assume such structure, then I need fewer observations n than the number of variables p. It seems magical, right? But you might ask, what is the secret sauce? Why would I be able to do that? Let's look at sparse vectors, right? So a sparse vector, so let's say I have a 1 million long vector, right? And I want to assume that that vector is 10 sparse. It's non-zero only in 10 entries, 0 everywhere else, right? So it's a 10 sparse vector, and but it has 1 million coordinates. So the question is this really high dimensional? If it is non-zero only in 10 coordinates, it lies in a lower dimensional subspace, right? It lies in a lower dimensional subspace of vectors that are non-zero only in those 10 coordinates, right? And so if I look at a 10 sparse vector in general, it's really in a union of 10-dimensional subspaces, right? And that same story generalizes to low-rank matrices, where the row and column spaces are lower dimensional subspaces, and so on. Okay? So the overall takeaway is that structure is really lower dimensional subspaces. It's really as simple as that. I have a higher dimensional parameter, right? 1 million dimensional parameter, and the structured parameter, I say that it has structure. If it really belongs, even though it's in a higher dimensional ambient space, it belongs to a lower dimensional subspace. Okay? And we can also answer other questions, such as, okay, here is a method which just minimizes a loss function, which measures the goodness of fit of my statistical model to the data. And again, so here is what a statistical model really is. It's a collection of distributions over random variables. Okay? So it's a collection of distributions over random variables. That's a statistical model. And what I actually observe are samples, n samples, from one of these distributions. Okay? So I have a whole bunch of distributions, and I observe samples from one of these distributions. And what I want to figure out is which distribution was it. That's really statistical model estimation. And a question that a lot of you have asked in one-to-one talks, and a lot of people keep asking, is how do I estimate the parameter theta star? How do I estimate the statistical model at hand? And so we have answered questions such as, okay, let's look at a general method which minimizes some goodness of fit measure, some loss function L, and some regularization function R, right? So what's a good R? And so this is something that we answer. Almost all statistical estimators in machine learning are really a optimization problem that minimizes a goodness of fit measure L plus some regularization R. Okay? So we answer what is a good R, what is a good regularization function, and also suppose you pick the statistical estimator here, how well would it perform? Right? How well would it perform? And so we have some really general tools to characterize the performance. So pretty much it simplifies a lot of our our jobs. So there have been literally hundreds of papers where for specific statistical models, for specific estimators, people characterize the performance. But now we have general tools to say when is it good, how does it perform, and so on. So the takeaway is that structure corresponds to lower dimensional subspaces. Okay? So there's been some other interesting work where they say that, okay, if it's a lower dimensional subspace, what's a lower dimensional subspace? I have few basis vectors, right? So if you look at the basis elements of my lower dimensional subspace, then I can even characterize my structured parameter using those. Okay? So there's been some follow-up work by Chandrasekhar and Recht and so on. What I'm going to focus on in the middle component of my talk is big N data. Okay? So big N data, what is big N data? It's this, this is blissfully empty, but really what is big N data? We have a lot of observations, right? And why do we have so many observations? So if you talk to a lot of folks in machine learning and statistics and so on, they say, okay, why are people suddenly talking about big data, right? Is it just another buzzword? Not really. So there have been advances in data collection technologies and data storage technologies. Okay? There's been a foundational advance. So we have all this cloud storage. We have a whole, especially in genomic sciences, we have next generation sequencing technologies which generate a lot of data. Right? And in a whole bunch of scientific applications, data is coming at us at a very high throughput. Right? So how do you handle this? And it's really driven by technology. So such a setting, I should note, is typically considered very beneficial to machine learning. So some years back, when I first started grad school in machine learning and TAing Carlos's class, this setting was said to be good for machine learning. Right? So if you have your model, graphical model, if I throw 1 million samples at you, that's good. I can now learn my model finally, right? So it's great. So I don't need to worry about structure, regularization, and all those other complicated lower dimensional subspaces and so on and so forth, right? Things are easy. But we should know that with great data comes great modeling flexibility. So as the data grows, our ability to model reality also increases. Right? So if I have simple problems or reasonably well-defined problems, then more data can actually help us. Right? So I can fit my model now finally. Right? But if I talk about things like our brains and modeling, say, the ventilation, movement of air in this room and so on and so forth, things are extremely complex. Then with more data, now I can fit a much more complicated statistical model. I don't need to do linear regression anymore. I could do some other complicated model that I didn't have the guts to do before because I didn't have enough data. Right? So literally, my model can grow with the complexity of, in complexity with the amount of data that I have. Right? So literally, you can never have too much data. The more data you have, the more complex a model is. So in some sense, you're always in a data-starved regime. And so the teleological endpoint of such complex models are non-parametric models, where you don't learn weights, or your parametric, or your components of your model don't lie in a finite dimensional space, but they lie in an infinite dimensional space. Okay? So you're learning functions instead of weights. Okay? So you give me 1 million observations, okay. Instead of weights, I'm going to learn functions. So that's all I will say. Right? So this seems like a great thing. Okay, so we can finally learn functions, which we couldn't before. Are we good? Right? Just learn functions, and we are all golden. The answer is no, because learning functions is really difficult. Okay, so let's even take 10,000 features. Right? To learn a function, 10,000 variate function, the number of observations I need will scale exponentially with the dimension. Okay. So if I compare parametric models, learning weights and learning functions, I need exponentially many more observations than compared to the parametric model. So that's not big N, that's infinite N, right? 2 to the 10,000. And 10,000 features is nothing, right? So maybe I can't learn functions, right? That doesn't seem like a reasonable thing. You might ask, okay, what can statistical machine learning do in the setting where you don't have infinite N, you have big N, right? You can learn functions, but you still need to think about how to learn these functions. We don't have off-the-shelf tools to do so. Okay, so what do? Can we use some of the insights that we have learned for big P data and apply that learning functions? And the answer is yes. And so again, so this was the big P stuff where I can learn a high-dimensional model with P weights if the P-dimensional parameter lies in a low-dimensional subspace or in a union of lower dimensional subspaces. Right? So that's great. And as you can imagine, with this notion of lower dimensional subspaces, all of such structure has focused on parametric models. So I have sparse models, low-rank models, graphical models, which again give you a graph structure over P variables. All of these have a finite set of weights. Right? Even if they are large, it's still finite. Right? And what I say is that these weights lie in a low-dimensional subspace. But in a non-parametric model, I have a function that lies in an infinite dimensional space. Right? So imposing a lower dimensional subspace constraint doesn't make any sense. Right? Something that I could do with a sparse model, I say, okay, 1 million features, it lies in a 10-dimensional subspace or a collection of those. I can't make such an assumption for a function, even something as simple as a function that has bounded slopes or something. Right? What can I do? So this is something that we did called sparse additive models that I want to talk briefly about. That goes a little bit to learning functions, okay, in the big N space where I have a lot of samples, but also I have a lot of features. Right? So I don't have just 1 or 2 features, but maybe I have 10,000 or so features. I still want to learn functions. Right? How do I do that? Okay, so let me talk a little bit about sparse additive models that we introduced that does do that. Okay? So here is the general non-parametric regression problem, okay, on the first line. So I have features x1 through xp, right, p features, and where p, again, think of it as at least moderate in size, 10,000, so potentially more, right? And I have a response y, okay? And I want to fit a non-parametric model, which is a function of all these p variables. So it's a p-variate function, okay? And so as I mentioned, if I want to learn a p-variate function, I need a lot of samples. So let me simplify let me impose some constraints. And so additive models are one way to constrain your p-variate function. Okay, so this is introduced by Friedman, Stwitzel, and worked on by many, including Hasty, Tibshirani, and so on. Here what you say is that your response y, right, think of housing price, stock price, whatever have you, any response, cancer incidence, and so on. You say that it's a sum of univariate functions. Instead of a p-variate function, it's a sum of univariate functions. Okay? And so that really simplifies a lot. Because each of these functions now only depends on one feature. So effectively what you're doing is you're learning transformations of your functions, right? And then you're fitting a linear regression model. But you're learning these transformations of functions. And so that's always huge in machine learning, right? Folks in machine learning are always suspicious of their features. So that's like their sore point, the kryptonite. They are always worried that their features are not good enough. But suppose I tell you that I can learn transformations of your features, and then you can fit a linear regression model. So that's what this does. Okay? It's an additive model. It's a sum of univariate functions. So what we then said was that, okay, so let's impose sparsity on this. My regression function is a sum of p univariate functions. Suppose I make the assumption that very few of these are non-zero. Most of the functions are identically zero. Right? Very few of them are non-zero. So this is a way of imposing some structural constraint, but for a non-parametric model. Okay? So this is what we call sparse additive models. And there's been a whole bunch of follow-up work on that, both on extending the analysis as well as other structured sparse extensions. And the idea of this sparse additive models is very simple, right? So it's a sum of univariate functions, but it's a sum of only very few functions. Okay? So that's the assumption, and that's it. It turns out that just this assumption is enough for us to learn functions with a lot of variables, right? And using very few samples. So here is the 3 bullet point summary of how you would estimate these functions. So what we really did was look at a population characterization of the regression function, right? So we asked, okay, I need to learn these functions. What's the optimal way? Imagine that I had infinite data, right? If I had infinite data, give me a way of estimating these functions, right? Simplified the algebra, simplified the expressions, okay? And then said that, okay, I don't have infinite data anymore, right? So let me look at these components and estimate these components using the finite data that I have. So it seems a bit hacky, but it turns out that we could actually give rigorous guarantees that we can actually learn the functions, right? What we got really is that we can learn functions or a lot of variables under some kind of sparsity assumption, okay? So we applied this to a neuroscience problem. So here is a cartoon for all of computational neuroscience. It just looks at encoding and decoding, okay? So what happens in a lot of neuroscience studies is that, let's take fMRI, for instance. So a person goes into this humongous scanner, right? And they're shown images, they're shown movies, they're shown words, string of words on a screen and so on. There's some stimulus, okay? Think of images. So the person is shown an image of a horse galloping in a farm. Then you have the brain, which starts grinding. And then the fMRI scanner measures the activity in the brain. Okay? So you have stimulus, which you can think of as the input, and then the neural response, which you can think of as the output. And so encoding is a problem of, given the stimulus, figure out what your fMRI scan should look like. Okay? So you can think of it as a computational model of the fMRI scanner. If you know how expensive those are, it'll be great if you can get that a great fidelity, but that's what encoding is about, right? Given the stimulus, try to figure out what the measurements, what the neural measurements would be like, okay? So that seems like, okay, why would I want to predict your neural measurements? Well, if you have an interpretable model, right? So remember that what's in the middle between the stimulus and the neural response? It's the brain, right? So maybe you can use some machine learning to do the encoding, look at the components and see, okay, maybe the brain also does something like this, right? So that's part of the reason why people are interested in encoding. And then you have decoding, which is a reverse direction, where given the neural response, you want to predict the stimulus. Okay, so that goes into territory of dream machines, right? So a person is in the fMRI scanner, just from the brain measurements, you try to figure out what are the images they are seeing, right? And so on. So creepy territory. But that's decoding. So I worked on this, but specifically for a portion of the visual cortex. The visual cortex is at the back of the head, and it's quite huge because that's the first thing that developed. Right? So it's at the back of the head, and then we have the prefrontal cortex all the way to the front. That's unique to humans. So what we looked at was measurements from the visual cortex, and a portion of the visual cortex called V1, which is, so this is a flattening of the brain, and that red portion is V1. It's a portion to the very back of the head, okay? And it's a visual cortex. So we looked at measurements in V1, and we wanted to solve these encoding, decoding problems, okay? So this is a problem. I have stimuli which consisted of naturally occurring images, right? And we looked at measurements in the form of fMRI measurements, frequency magnetic resonance imaging. All of this was from a single postdoc who was in the scanner for 200 hours, which is why we had so many observations and we wanted to do encoding and decoding. So this is what we came up with. Okay, so we did both encoding and decoding, and so this is what we came up with. So on the left you have the image, the stimulus, and on the right you have the fMRI measurement, and in the middle is a model. So what we really did was we took the image pixel values, okay, just the raw pixel values, and then we tried to mimic what's going on in the visual cortex. Okay, so because it's the V1 is an early visual cortex area, people have studied that a lot, right? Close to a century, and so they know what are some of the cells that are early on, that occur early on, and those are called simple cells. Okay, so which largely behave like edge detectors, roughly. They're more complex, but you also have something called complex cells, which again, what people say, a reasonable model is that it pools together. It's a linear combination of simple cells. Okay, so people have models for really some simple cells, or simple and complex cells in the visual cortex. So what did we do? We said, okay, let's take these filters, simple cell, complex cell filters, and try to learn transformations of these, right? So we know how to learn functions, even when I have a lot of features, right? And reasonable number of observations. We know how to learn functions, so let's learn transformations of these very simple and complex cell models, okay? And then pool all of that together, that's the big plus, and predict the fMRI signal, right? So it's a very simple, almost linear regression, but except that I'm learning functional transformations of standard filters. And so let me show you some plots on how well we did. So I'm going to show you the R square, which is the correlation of the predicted fMRI response and the actual fMRI response. And we compared that to standard sparse linear regression, right? So which is something that you would do in higher dimensional settings, right? So I have a high dimensional linear regression. Let me fit a sparse linear regression model. So we compared it to that, and so here are some plots. Again, so I'm plotting the R square, the squared correlation. So on here, so we called it VSPAM for visual cortex sparse additive models. Maybe that's what the brain is doing, who knows. So we have the VSPAM on the y-axis, sparse linear regression on the x-axis, and you can see that we perform strictly better. Okay, so remember that I'm learning functions, transformations of some complicated filters. So it's amazing that we were able to do so, and able to do so in a systematically better way. Okay, so here I show you the relative improvement, and you can see that we improve by quite a bit. And so here I'm showing you some of the functions that we learned. Okay, so again, remember that I have certain primitive models of cells in the brain, right? But I don't really believe those simple models. So what I really want to do is learn transformations of those simple models, right? And so these are some of the transformations we learned, and you can see that all of them are really saturating, right? So they increase, they are linear, monotonic, and then they saturate, right? And so this makes sense to neuroscientists, right? So one of the, they were distressed by simple and complex cell models because they were just linear pooling of the image features, right? But you don't want to do that because the neurons, right, even simple and complex cells, they're going to saturate at some point. So you need to take the pooling and you need to saturate them in this way. So they were quite excited by looking at these transformations, which you just learn from data, right? So we can learn functions. It's, again, something similar where I have a stimulus, right, image, and I'm modeling the retina. Okay, so I have a retinal ganglion cell, which is something I can measure from. These are measurements from cats. And I have rods and cones, right, which is also something I can measure from. But you have certain other cells in the brain, in the retinas, called bipolar cells, which are difficult to measure from. Okay? So again, in the retina, I can measure from some cells, I can't measure from some other cells in the middle, and I still want to fit a model. Right? And so what people really think these cells in the middle, called bipolar cells, are that they pool together the cone outputs, and then they learn, and then there is a transformation, a nonlinear transformation, right? And so here again, we could apply our sparse additive model technology to learn transformations. And once we learn these transformations, we can then go to these folks and say, okay, here is a transformation. Is there a scientific basis? Is this how bipolar cells will behave, right? And so this is some application that we are currently working on. So I'll just put it out there without going into further details. Okay, so what I largely talked about was learning sparse additive models, right? Which essentially are learning functions in high dimensional regimes. This is something that people didn't think you should be able to do, right? So you have 1 million features, you shouldn't be able to learn functions, right? But you can, right? Under a sparsity assumption, which is great. But I should note that a unified story of the kind that we developed for parametric models is still outstanding. So that's, I think, something that's going to be quite exciting, where if one can develop such a unified story for learning functions with lots of features, that would really solve our feature construction problem, feature fidelity problem, right? In a lot of engineering applications, features are so important. If I can learn transformations willy-nilly, I'm golden, right? So I think it'll. So I just showed you a couple of examples where learning features really helped, and I think it's something that is going to hold across science and engineering, learning features. And we can do that in a systematic way, neat way, if you will, using non-parametric models. So let me spend just a few minutes on what I call complex data. Maybe I should call it big Q data, but maybe not. What is complex data, right? So it looks like this. It's quite complex to look at, but it's things like phylogenetic trees, right? So the tree of life and so on. So you have all these species, and maybe there are some ancestors, and I need to really figure out the phylogenetic tree and then explaining all the different species, right? And you can have similar hierarchical trees even to explain grammar and syntactic structure in text, right? You have parse trees. And then you have that image on the right, which even I don't know what that is. It's some kind of mind mapping thing, but it's a huge graph, right? And such complicated graphs are complicated structures, right? So all of these are complex data types where even if it doesn't need a lot of weights to specify, right? So phylogenetic trees, it doesn't need a lot of weights to specify the tree, right? But it's still complex because it lies in a large discrete space. Okay? So it lies in a space. Think of it as a bag of objects, and there are too many such objects, combinatorially many, right? And so things get tricky. And so permutations and rankings is another, right? So web search is huge, billion-dollar industry. And what it really solves is the ranking problem. You search something, right? What Google and Microsoft and so on, what they want to do is, given the set of all possible documents, they want to give you a ranking of relevant documents, right? So ranking is one such. Another data type, which again lies in a large space, right? So permutation of n objects have n factorial many permutations, right? So a lot of them, and so let me talk, I guess, spend a few slides on ranking, because that's something that I started working on. And rankings have applications not just in web search, but they have applications even in sciences, right? So if you talk to chemists, they say, okay, give me a ranking of these molecules in correspondence with some measure that they care about, right? They don't just want you to predict something. What they really want is a ranking, right? So this happens across science, and of course, recommendation systems, tracking, which is something Carlos has worked on, and so on, okay? So ranking is a data type, permutations is a data type that is becoming increasingly important. So I have m objects, and I need to output a permutation of these m objects. And this huge number of words are really all the different methods that have just come up in the last 5 years for different ranking methods for web search, not just web search, but ranking documents. Okay, so there's been a sudden explosion in extending machine learning to the ranking problem, okay, to the supervised ranking problem. And as you can imagine from all these different methods, it's just starting, and a systematic statistical machine learning theory is still outstanding. Okay, so what do I mean by that? And it has to do with the sad tale of no loss function. Okay, so when we think about machine learning, in fact, sometimes I go give a talk at different departments, and they equate machine learning with classification, which is trying to predict a binary outcome. And if you say that that's not all you're working on, they say what you're working on is not machine learning. But for a while, a lot of supervised machine learning, at least, an important component, let's say, is binary prediction, right? Binary classification, where I'm predicting a binary outcome. And for this, there is a very natural loss function, 0, 1. You either get the binary outcome right or you don't, right? Okay, so is the stock price going to tank or it's not, right? So if it's a binary outcome, you either get it wrong or you don't. So the loss function is very clear. And based on this, a whole theory for machine learning has come up for classification. Okay? So there's a whole mountain of theory, all based on this loss function. Okay? So you might say that, okay, so I thought in machine learning, if you just give me a loss function, I can do machine learning, right? But no. So if you look at machine learning theory, right, in terms of giving guarantees for whether you're doing the right thing, a loss function is critical. Okay? So given the loss function, then they work on it, try to see what it's comprised of, coming up with optimization methods, and so on and so forth. Right? So in fact, there's also a lot of work on devising surrogate loss functions, where I don't really optimize the 0, 1 loss. I try to come up with new loss functions which mimic it, and so on and so forth. Right? And unfortunately, in ranking, there is no agreement on the true loss function. Even for something as simple as web search, there is normalized discounted cumulative gain, right? And then Yahoo recently came up with the expected reciprocal rank. So they had a whole ranking challenge where they said that this is our new measure, optimized with respect to that, right? And then you have standard things like area under the curve, average precision, and so on and so forth. And of course, statistics has a lot to say about the metrics you should use. And what do we do, right? So there is no standard canonical loss function. So we need a new way of doing statistical machine learning. I'm not going to fix the loss function, right? I need a way to be nimble in the face of multiple loss functions. And this is going to be something that's true for most complex data types, right? It's really a facet of the complex data type, because ranking is so complex that people cannot agree on when are two rankings similar. A systematic constructive theory for how to approximate such functions, a unified analytical framework for how to learn rankings in the presence of multiple loss functions, and so on. So Big P, okay? So Big P data have lots of features. What we have done is a unified framework for characterizing what structure means, okay? So high dimensional model, hopefully it has some structure. What does this structure mean? And given this notion of structure, how do you estimate the high dimensional model? Okay? So a unified framework for all of these, both to analyze and to characterize. Right? And how to pick regularization functions. This is something that everybody asks. We have now answered, at least to a reasonable degree, these questions. But what's remaining? Right? And what's remaining is to extend the notion of structure from what I just described, which is really a union of low-dimensional subspaces, that captures where we have gone till now, right? That captures where we have gone till now, but it doesn't really capture some of the more exciting things. For instance, in the virus thing that I mentioned, suppose I want to know the structure of the HIV virus, right? So that's a 3D molecule, right? So it's not sparse, it's not low rank, right? What is it? So maybe it has some structure like a ball with some spikes, right? That's structure too. How do you encode it in a mathematical language and learn the model, right? So that's something we are working on. And we have a very good idea on how to do that. And also something what I call heterogeneous structures, where it's like a Lego block. You have some structure here, some structure there, and so on and so forth. You combine all of these structures, just as you combine Lego blocks to create something very complex. Can we have such a story for high-dimensional statistical estimation? Answer is yes. To take all the stuff we have done in machine learning and extend it to computational science. Okay? So there's this whole community of, almost all of science. If you look at civil engineering and so on and so forth, what they work on are complicated systems, but where they have a mechanistic model. You can even look at physics, chemistry, and so on. They look at some flux equations, right? If you talk to somebody working with aeroplanes, they have some complicated PDEs, right? So they have these complex mechanistic models, right? And they still want to do prediction. They still have data. They still want to do prediction, but that's still very, very different in character from what people have been doing in machine learning. And then we have big N, where we said that, okay, I can learn functions, even over lots of variables if I have lots of samples. So I did mention that we do not have a unified framework for imposing structure on a p-variate regression function. We don't have a unified story yet, right? It's because the research is just started. And one other thing is sublinear algorithms leveraging computational geometry. That's another exciting thing. That what we did was reduce large-scale statistical estimation to some computational geometry questions. And so modular preprocessing, we could estimate these statistical models in sublinear time. And of course, complex data. And so this is really a virgin field where a lot of questions, people really want to understand how to do statistical machine learning for complex data types, and something I'm working on. Thank you.